Hello, we are Group 14 and we will be presenting our Motor Assisted Cooler or MAC. Our group consists of 2 computer engineers, David Crumley and myself, Min Park, and 2 electrical engineers, Akil Ahmed and Fong T.E. Dong. The overview of this presentation is to design and finish our project with the time remaining, which consists of our motor assisted cart, the Peltier cooling device, and our solar charging unit. To test our refrigeration device, we used a styrofoam cooler with internal dimensions of 12 3/8 by 10 3/8 by 10 1/8. It should also be noted that our prototype cooler is considerably smaller than the cooler that we will be using in our final design. The following video demonstrates our refrigeration device and its relay system. We set the temperature to 15 degrees to show that the relay cuts off the current to our system, and then if the temperature rises above 17 degrees, it turns back on. Here is the data we collected from our prototype cooler. We tested out how cold it could get down from the inside of the cooler from the ambient temperature within 30 minutes. With nothing inside, it got down to 47 degrees room temperature, and with a cold cup of water inside, it went down to 41 degrees.
So the motors are attached to the wheelbase with custom-made aluminum brackets that were designed to fit the motor and the wheelbase perfectly. The torque is transferred to the wheels using belts and pulleys. We've gone with a 3-to-2 teeth ratio, which will add more torque to the system. In this picture, we get a more close-up angle of the drive assembly. We see the larger pulley is attached to the wheel with epoxy. The smaller 20-teeth pulley is attached to the shaft of the motor using a set screw. We went with the 6mm timing belt, the same ones used on 3D printers for this design. In this slide, we can see the software that was used to test the drive system. We first started out by setting the PWM to 60 Hz signal, which we found was the best to use with DC motors. The address value holds the ADC input value. CCPR is used to control the duty cycle, while the output polarity is controlled dependent on which GPIO is used to send the PWM signal to the circuit. In this slide, we're going to see a video of the testing procedure taking place. As I move this potentiometer, the speed and direction of the wheel changes. This is exactly what we wanted to see, everything held together, so we can move on to further testing. Once the PCB came in the mail, we decided to solder it all together. One thing we found after some extensive testing was that the symbol used for the transistors in the Eagle schematic had the drain and source pins reversed. What we're going to do is adapt our MOSFETs to work with this new schematic, and everything should work fine.
We tested our final PCB last week, and as it can be seen in a video, we attached our battery with a solar charging circuit and the solar panel, and we reduced the voltages of solar panel from 17 to up to 12, and the current that is going into the battery has increased. We haven't implemented the maximum power point tracking algorithm yet, but since we checked our hardware, we read our current data, we read our solar data, battery voltages, and even we created a PWM with different duty cycle, and it behaves the way it should. The only thing that is left to implement the maximum power point tracking, and we are working on that algorithm, and it will be done pretty soon. That's all from solar charging circuit right now. Here are some chunks of a code that we are basically using in our charging circuit. We already read our voltages, current, and generated PWM using different duty cycle, and it shows the result that we expected from a hardware side. We are working on PWM algorithm. After that, we also working on a code that shows the state of a battery at any particular given time. And these are the functions that will be called again and again in a loop. And based on the voltages and current, we will change the duty cycle so we can come up with a maximum power point tracking.
The following video is of our Peltier cooling system and solar charging circuit connected to two batteries in parallel. The LCD displays voltages of the batteries and the solar panel, and the current that is going into the butt converter, and then the current that is going into the battery from there. Due to the cloudy sky, we were only able to get around 17 volts from our panel, which was not ideal during our recording.
We've been trying to implement different circuit designs to our project and make some adjustments according to the issues. The photo below is showing all of the unsuccessful PCBs that we have so far. Many parts of our circuits were burned out due to the high currents and inappropriate soldering and wiring. However, we were able to identify the problems and proceed to make better PCBs. The next steps that we should be doing is completing the code for the MPPT solar charger. We also have to finish assembling the handle and the PID controller. Finally, we have to integrate every separate part on together. Thank you for your listening.